Okay, first of all, welcome to the course of liquid chromatography and mass spectrometry. And it's a pity we cannot start this semester in lecture hall in person, but there are other events taking place, and therefore it's online only today. But mostly it will be still in person in lecture hall. Okay, so let's jump to the slides. And first, a little overview of the course. So it's a course about liquid chromatography and mass spectrometry and at advanced level. So we have a look at chromatographic process and the models which are used to describe it. We also discussed the principles of liquid chromatography and mass spectrometry instruments, to some extent cover sample preparation and also ionization methods used in mass spectrometry. Then column chemistry, column types, and liquid chromatography types will be covered. We also see how the methods are developed and validated. Indeed, validation in very briefly, but still a little comment will be made on this. Then we also cover mass spectrometry, not only the usual low-resolution mass spectrometry, but also high-resolution mass spectrometry. And there will be some other topics, for example, isotope ratio mass spectrometry, ion mobility spectrometry will be covered also. And for this course, we expect the preliminary knowledge at the basic level of liquid chromatography. So if you have passed the courses of analytical chemistry, the general ones, then this should be sufficient. Now, the course materials are in Moodle. As you are here, then you probably found all those materials. And I promised to keep an eye on my phone that nobody has said that they have problems joining, so everyone should be here. The lecturers will be then Riin Rebane. She will mostly discuss the practical aspects and sample preparation for liquid chromatography. Then Georg Arju will cover mostly high-resolution mass spectrometry and ion mobility spectroscopy. I will focus on liquid chromatographic methods and also mass spectrometry with low-resolution instruments. And Ivo later will join when something goes wrong or there are some topics that he can cover. So, as this toolbox here covers part of the text of the slide, then I will switch off the camera. And let's hope that now, yes, now it's much better. So we will work in lectures mostly, but this lecture is not just a lecture in the way that I talk and you listen, but you are very welcome and to ask questions, to initiate discussions. So please, when you feel that there are something that requires more explanation, feel free to raise the question right away. and we can discuss it, and the lecture will be transformed to seminar on the go, and then when this is discussed, then we continue in a lecture mode. Of course, it will the course will also have quite a bit of independent work, whether completely independent on or in small groups, then we will see during the course, and there will be both ways. And in brackets, I added two additional modes. One is called Remote Lab. And this remote lab means that in the lecture hall, we take control over the computer which runs the real chromatographic experiments, and do the experiments all together directly from the lecture hall. So this is something that which will be definitely done for those students who also participate the practical course, so the laboratory course. So we will make this remote lab with those students, but everybody else is very welcome to join. So this kind of remote lab session. And why is it helpful? Because what we see very often here is that if we start making experiment in liquid chromatography, then most of the effort and most of the time we will spend on learning the chromatographic software. So we don't deal with chromatography, we deal with software. We try to find out where to change the flow rate, where to change the wavelength of the detector, or where to change the eluent composition. But this is much easier if we do it all together in lecture hall. It's more effective then, and you can learn the software by seeing it on the screen, and then you are more familiar with the software when you go to the lab yourself. Okay, and then this small laboratory part as part of this course. This is possible. Last year we had it to a limited extent, but still, yes, we had it. Those of you who took those students who took the laboratory course, they didn't benefit much, I would say, because it pretty much repeats the laboratory exercise. But it also has another part dedicated to high-resolution mass spectrometry, and this is useful, and this we also managed to organize last semester or last year. So this will be somewhere in May or June. So this is not something that runs during the semester. It will take place in May or June. Okay, lectures start at 2:15 on Mondays, and Wednesdays also 2:15. Note that the rooms are different. So 10:20 on Mondays and 10:21 on Wednesdays. And as I said, the practical lab will be in May or June in small groups, and those who really wish to take it, this is a voluntary, it's an optional part of this course, and by no way it influences your grade in the exam. not directly. Of course, the knowledge obtained during the practical session, this may have influence on your grade. But there will be, or perhaps will be two labs, one for LCMS and another for high-resolution MS. Okay, questions so far? I don't see any questions. Then please, everybody, write hello in this message box. Just that I see that you are there, and yeah, hi. Okay, wonderful. So still the microphone is working. That's great. Okay, very good. Then it also means that you know very well where the message box is. So you're very welcome to write all your questions there and comments. So yes. Okay, let's continue. The program is available in Moodle. You can have a look at what we have planned for this course. Then also what we have this year is the planned sequence of lectures. We try to stick to this sequence, but well, the semester is long and quite some changes are possible. We try to go according to the plan, but if something happens, then some other lecturer might jump in with his or her topic, and therefore some fragmentation of the topics is possible. We try to avoid it in as much as possible, but it is still can happen. Okay, and as I already mentioned, then some parts may be left for independent study or group work. And it may even happen that we have to leave some parts out. And the reason for leaving something out is if the discussions during the lectures are so long and intense that we don't manage to cover all the material, then we leave out this material. And of course, this material will not appear in exam in that case. All right. One slide from COVID times that is now extended to all other illnesses as well. So throughout the semester, the lectures, seminars, and even this remote lab will be broadcasted by this big blue button tool and also recorded. So if you feel ill, then please don't come to the class. Even if the illness is something other than COVID, still better not to risk to spread the virus or any other illness. So as the online lectures are available, then I think this is not a problem. Okay, sometimes as today, we purely rely on the lectures in Moodle and Big Blue Button, and this may happen if the teacher is ill or maybe sometimes traveling somewhere and then delivers the lecture remotely. Now, information exchange is based on what is said in the lectures in the classroom, and so we assume that everything that is said in the classroom that everything knows or has heard it. So this applies to the lecture material as well as to the organizational questions. So homework or exam times or information about the coming lectures. So if it's said, then we assume that you have heard it. Sometimes we also repeat it in written form via Moodle forum, but not always. So be careful, visit lectures or listen to them online. And if you cannot be present, then ask your friends what was important, what was told in addition to lecture materials. Of course, watching recordings gives also all the information. Sometimes lecturers forget to switch on recording, then please remind them about starting to record. Of course, if you only watch recordings, then you cannot ask questions online, but you can ask questions in Moodle forum after the lecture. So if you have questions during watching the recording, then feel free to post the question in the Moodle forum. But unfortunately, the organizational decisions that we make during the lectures, then you cannot participate in this decision making. And those of you who didn't receive email yesterday from Moodle stating that that the lecture is just online today, then please check that that your email address in Moodle is correct. If it is correct, then please let me know that there is an issue with receiving emails, and we will try to check from Moodle side if something is wrong. But double check your email address in Study Information System, because your information is transferred from Study Information System into Moodle, and this happens every night. So if you try, I'm not even sure if it's possible, but if you manage to change your email address in Moodle, then next morning it will be back to the previous one, to the email address that you have in Study Information System. So check it in the Study Information System. The course will end with an exam. It will be online, so Moodle exam, without the usage of materials, so-called closed textbook exam. There will be clickable questions, which can be multiple choice or ordering or yes/no questions. And there will be also essay type questions where you type text into a text box, and explain the concepts or compare techniques or choose some suitable method for analyzing some compounds. And the exam grade will be based on your performance on this exam work. So it doesn't show your effort or how often you visited lectures or your preliminary knowledge or progress. So it's just what you have written in your exam work. This is what we evaluate there. Okay, and we cover several topics in liquid chromatography, so separation mechanisms, some normal and reversed phase, size exclusion, ion chromatography, the models, we just mention affinity chromatography, but don't explain it much. Then stationary phases and columns used in liquid chromatography, also equipment used for analytical liquid chromatography. Also, method development and optimization of liquid chromatography is discussed, and to some extent sample preparation. Concerning mass spectrometry, we have a look at the design of mass spectrometers and also ionization methods. Then vacuum. Vacuum is an important part of practical use of mass spectrometers. So vacuum pumps and vacuum measurement devices and pressure measurement, then this is one part of the course. Of course, liquid chromatography and mass spectrometry can play together, as the course title implies. So how they play together, then we will also see this. We cover applications, or some examples of application to be more precise, for chemical analysis and identification and structural analysis of compounds. Also, high-resolution mass spectrometry, isotope ratio mass spectrometry, and ion mobility spectrometry will be covered. Okay, that much for introduction. Any questions or comments? I don't see any. So you can say no, then I know that you still hear me. Okay, yes, I see that you are typing, so it means that you heard. Well, indeed, it's still a bit odd to just talk to a computer and not seeing the people I'm talking to. So the communication is good. All right, but let's go to our first topic is introduction to chromatography. And here we will deal with the mathematical models for the description of chromatographic process. And here we see what factors play a role in determining the retention time in liquid chromatography, why peaks are sometimes broader and sometimes narrower. Maybe also see why peaks sometimes are asymmetric and how to describe this asymmetry of peaks. And also why partition chromatography is more popular than adsorption chromatography. So perhaps from earlier classes, you know that the reversed phase liquid chromatography is the most widespread one, and this is the type of partition chromatography. And this feature of being partition chromatography plays a role in its popularity. But we will see it in more detail. Okay, so we consider retention time, peak width, and peak shape in the chromatograms. And those two chromatograms here show some tailing peaks, or on this one, some quite broad peaks, and well, there are some narrower peaks. And also the retention time is quite variable in those. So let's see what factors affect those quantities. Okay, before the start of the lecture, I mentioned that I made a couple of changes to those slides. And here is the slide where I made a change. And earlier, their mobile and stationary here were painted, or the font had color. Now I made it black color, just because this color indicated wrong things in the scheme. So this was the change that I made. Okay. In this partition chromatography, this is about liquid-liquid chromatography, and partition takes place between two liquids. And this is the most common way of using liquid chromatography, that our stationary phase is in the form of a liquid on top of a solid carrier. So we have a solid carrier, solid, let's say, nucleus. And quite often it's silica gel particle, and this is indeed solid. And on the surface of this solid carrier, some liquid stationary phase is placed. This liquid may be just adsorbed on the surface of the solid particle, or, which is more common, it's covalently bonded to the solid phase. So this stationary phase is in fact this blue liquid layer on the surface of solid carrier. So this solid particle itself, the solid interior, this does not function as a stationary phase, just the surface layer. And the surface is covered with liquid. And yeah, sometimes it doesn't look like liquid, but we consider it as a liquid. Okay, so liquid stationary phase on the surface of solid carrier. Where is the mobile phase then? Well, mobile phase is not shown in this scheme. So mobile phase could be just a liquid coming down and going, just passing the liquid stationary phase. So mobile phase is another liquid and passing this in the neighborhood of this stationary phase. And molecules, we may say analyte molecules, those distribute between the mobile phase and the stationary phase. To some extent, they are in stationary phase. So at the moment, 1, 2, 3, 4 particles or 4 molecules, and also 4 molecules of the analyte are in mobile phase. Okay, similar thing also may happen in gas-liquid chromatography. Mostly this is the type of gas chromatography used nowadays. So the liquid phase layer on the solid carrier is inside the capillary column in gas chromatography, and the analyte molecules partition between the gas phase and the liquid stationary phase. So in this case, when the stationary phase is liquid, then gas chromatography, liquid chromatography are just different from the point of view of what is the mobile phase. So mobile phase in liquid chromatography is liquid, in gas chromatography is gas. All right. Why I also make a note about this gas chromatography and gas phase here, because we will talk about Henry isotherm, and this is about equilibrium between the gas and liquid phase. This we will see in a few slides. Okay, then another type of chromatography is adsorption chromatography. So adsorption chromatography. And in that case, we have the stationary phase. And in this case, the stationary phase is the solid particle, or more precisely, the surface of this solid particle. It can be also silica gel, but now it's not covered with anything. It's just the bare silica, and the silica surface serves as a stationary phase. And again, it can be used in liquid chromatography. Then we call it liquid solid chromatography or liquid adsorption chromatography. And adsorption from liquid phase to the stationary phase surface takes place. In case of gas chromatography, it's gas-solid chromatography, or sometimes simply adsorption chromatography. And in that case, molecules from gas phase from gas phase, they adsorb on the stationary phase, on the surface of stationary phase. Okay. Any question or comment so far? Okay, then if you don't have questions, then let me ask. This solid stationary phase particle here is drawn as a, let's say, solid circle. Let's say it's simply circle. But real stationary phase particles have pores. Do we speak here in those slides? Do we speak only about the outer surface of the sphere, or also the surface of pores? You can simply type outer or pores. Okay, both is one with question mark. Okay, both is also good answer. Pores, yes. All surfaces of stationary phase. Okay, very good. I don't see anybody writing anymore, so yes, you are right that not only the outer surface, but also all the pores that the particle may have. And this applies to both. In case of liquid stationary phases, also those solid particles, they have porous structure. There are many pores, usually even the pores which penetrate through the whole particle. And all those internal surfaces of pores, they also are covered with stationary phases, stationary phase molecules, and participate in those partitioning processes. Or in this case, they partition in this adsorption process. So yes, the particles are drawn spherical only for simplicity, and the pores have been omitted. All right, now let's consider that we have liquid phase and we have gas phase. And certain molecule, and this type of molecules we denote it by I, this lowercase I. This molecule can partition from gas phase into the liquid phase. And this kind of equation holds that the concentration of compound in liquid, this Ci, equals some constant times the partial pressure of the same compound in gas phase. So partial pressure of the compound in gas phase, we may think of this as a concentration. So partial pressure is similar to concentration of liquid substances or substance in a liquid phase. Okay, I think I perhaps tried to explain it. So let's have a text box here. So you definitely know ideal gas law. This is familiar to you, I'm quite sure. But now if we take that P equals N divided by V and then RT, then we see that this N divided by V, this is the number of moles divided by volume, which is similar to concentration, which is the molar concentration. And partial pressure is an analog of this. So just this RT is the let's say the constant factor there. So just to demonstrate that this partial pressure is similar to concentration, molar concentration. Okay, so in short, there is a linear relationship between the molar concentration of compound in gas phase and in liquid phase. If the gas phase and liquid are in equilibrium, so molecule is given enough time to partition between gas and liquid phase. All right, now if we take two liquids, then very similar formula holds. So Kd is the distribution coefficient, and we've got two liquids here, liquid 1 and liquid 2 and liquid 1, and the compound I distributes between those two liquids. And the ratio of those concentrations, concentration of the compound I in liquid 2 with respect to concentration of the same compound in liquid 1, this is constant. So this is characterized by the distribution coefficient, this K with index D. And we can write it or derive it similar to the Henry's law. So Henry's law or the partition or distribution law, those are mathematically very similar to each other. Both of those relationships, they give a linear relationship. So linear absorption isotherm, and very often it's called just Henry isotherm. So even regardless whether gas or liquid phases are dealt with, still Henry isotherm is quite often used. And we see that that this is the linear relationship between the concentration of the analyte in mobile phase and with respect to its concentration in the stationary phase. So the higher is the concentration in mobile phase, the higher will be it in stationary phase, with the factor being this K. And this linear relationship or linear absorption isotherm is one chromatographic model, and we call it linear chromatography. And it describes the partition of analyte molecules between stationary and mobile phase, and this linearity is something that we really want to work with. If possible, then we try to use the chromatographic conditions such that as to promote the linear relationship. And in partition chromatography, it's easier to achieve this compared to adsorption chromatography. In case of adsorption chromatography, this linearity is difficult to achieve. All right. Now, what are the prerequisites for the linear chromatography model to hold? First, both the stationary phase and mobile phase must be homogeneous. And as both are, if they both are liquids, then liquids are quite nicely homogeneous. And therefore, liquid-liquid partition chromatography is the way to go if we really need the linear chromatographic model. And why is it important, or how do we know it? Then there must be no possibility that molecules of the same compound interact with different strength in one phase or another phase. So the strength of interaction with solvent molecules or the phase molecules must be the same. And also the volumes of the stationary and mobile phase must be much larger than the amount of compound. So if this does not hold, if we have high or very high concentration of the analyte in either of the phases, then the molecules become interacting or start interacting with each other, and then the strength of interaction of molecules is different. So the higher concentration brings about nonlinearity in those models. Well, how well do those conditions hold? In reality, just partially, but it's not too bad. If we are careful and do not exceed certain concentration limits, then it still holds. All right, now let's focus on liquid chromatography and write the equation for liquid chromatography. So the same distribution coefficient, Kd, and now we see that the concentration of analyte in stationary phase is divided by the concentration of analyte in mobile phase. And from this point on, we will quite often use abbreviation stationary phase SP and mobile phase MP. So stationary phase, mobile phase. So this kind of ratio of concentration, analyte concentrations in stationary divided by mobile phase, this is the distribution coefficient. So this KD depends on the compound and of course the liquids, the chemical nature of those liquids and the phases, but not much on the temperature. So temperature is not that strongly affecting this KD. All right, now let's rearrange this distribution law, and we rewrite the concentrations as the ratio of number of moles of compound and divided by the volume of respective phase. So volume of stationary phase, volume of mobile phase. And now if we rearrange, then we find that the number of moles of analyte in stationary phase divided by number of moles of analyte in mobile phase equals KD times the ratio of volumes of stationary to mobile phase. And both of them equal the capacity factor. Well, capacity factor is the old name. Retention factor is a nowadays used term for this. So retention factor for the compound I is given by the number of moles of analyte in stationary phase to the number of moles of analyte in the mobile phase. Okay, it depends on the compound, it depends on the chemical nature of phases. Of course, it depends on the partition coefficient KD and volumes of phases. So we see that this retention factor depends also on the volumes, or more precisely the ratio of volumes of stationary and mobile phase. Okay, now if we go further, then as we know, the retention factor can be derived from the chromatogram, data from the chromatogram, and then we can make them equal. So the retention factor equals the KD times ratio of stationary and mobile phase volumes, and this equals to this ratio of retention times. Just as a reminder what those retention times are, then this TR is the retention time of the compound I, and Tm is the void, or sometimes said also dead time, and this formula is for calculating the retention factor. Now, if we rearrange the formula, then we arrive to the main equation of elution, which relates the retention time of a compound I to all the other quantities. We see that retention time of a compound depends on Tm, the void time or dead time. Then it depends on the KD, the distribution coefficient, also the ratio of stationary and mobile phase, and that's it. And now, if the question is which factors contribute to higher retention, so if we want to make a retention longer, just TR bigger, so what should we do? And first thing, if we look at Tm, then Tm can be made longer, or Tm can be increased if we make the mobile phase flow rate lower. So the lower is the mobile phase flow rate, the higher is the Tm. Of course, if Tm is bigger, then Tr is also bigger. Then Tm is also bigger if the column is longer. So also longer column increases the retention time. Now, if the partition equilibrium is shifted towards stationary phase, then this means that Kd is higher, and if Kd is higher, then retention time is bigger. And well, we could also have said that if the equilibrium is shifted towards stationary phase, then it means that the compound stays relatively longer time in the stationary phase, and indeed the retention time is longer. So no wonder here. Now, the larger is the stationary phase volume. Okay, the more stationary phase is present where the analyte can distribute, quite logical. And the lower is the mobile phase volume, well, also quite understandable. Okay. So this was about the retention time of a compound. Now our next question was about the peak width of compounds. And peak width increases during elution. So if peaks are broader, peak width is bigger, peaks are broader, then separation efficiency is lower. And we know that this is described by Van Deemter equation. There is a question. How can we change the volume of stationary phase? Okay, good question. Is there anybody who would suggest an answer to this question? Yes, different column, but what could be different in this column? Silica, okay, but silica itself is just a carrier. So what can we make? How can we make the volume of this stationary phase bigger? After the time could be less volume. Well, no, it's not about the volume of silica. It's about the volume of this liquid which covers the silica particles or the silica surface. Length of the column, yes, this indeed increases the stationary phase amount, let's say, which means volume. Column diameter. Column diameter, yeah, to a certain extent, yes. Are there different options of stationary phase? Yes, there are many different options for the stationary phases. Stationary phase thickness, yes. Indeed, if we think of a type of chromatography where the liquid phase is not bonded to the silica gel, but it's just adsorbed, then different amount of liquid can be adsorbed on the surface of the liquid, and the bigger or the thicker is the layer, the bigger is the volume of the stationary phase. indeed. And yes, there are different stationary phase options available. We will speak about them, I would say, maybe after 5 lectures, approximately. Okay, can we regard that this question is answered? So, okay, yes. All right, then let's go back to peak width. So peak width increases during elution. We will see this. And Van Deemter equation relates the height equivalent of a theoretical plate, so this h, to several factors, let's say. And, the formula is on the following slide, on the next slide. But here we just want to see what this h is and how is it related to the number of theoretical plates. The number of theoretical plates is quite a well-known parameter for describing chromatographic efficiency. So number of theoretical plates describes the chromatographic efficiency, but the height of the theoretical plate, this h, is inversely proportional to this number of theoretical plates. So it means that we can use either of them to describe the efficiency. Just we have to know which way they change. We know that the higher is the plate count, so the higher is the number of theoretical plates, the better. The more efficient the chromatographic process is, the narrower the peaks are. And if n is bigger, then h is smaller, so the smaller is h, the higher is the efficiency of chromatographic process. So we can think of this relationship between h and n in terms of the column length. So this is the length of column with uppercase L. And if we calculate the number of theoretical plates, then all those plates should fit within this column. They are equidistant, and if we then divide the column length by the number of theoretical plates, then we obtain just the height of one plate inside the column. So if n is big, then h is small. Very simple. Inversely proportional. Okay. Now let's see the Van Deemter equation. And this is a bit simplified form, but still very useful. So the height of the theoretical plate, h, or the chromatographic efficiency. This depends on this A, which is eddy diffusion. If it depends on B, which is longitudinal diffusion, and then two C terms. Those are the mass transfer coefficients or mass transfer terms, and respectively in stationary phase and mobile phase. And this lowercase u is the mobile phase flow rate. And what we get from here is how the efficiency, chromatographic efficiency, depends on the flow rate. And here is the experimental curve. We see that if the velocity or the mobile phase flow rate is very low, so very slow flow through the column, then the height of theoretical plate is big, which means the peaks are broad and chromatographic process is not efficient. Now, if the chromatographic flow rate, the eluent flow rate is very high, then again the peak the plate height is relatively high, and again the peaks are relatively broad. And only in this range, the mobile phase velocity guarantees that the efficiency is the highest, which stands for the lowest height of the theoretical plate. So low theoretical plate means that column has higher number of theoretical plates. Okay, how those terms in this equation, how they depend on the flow rate. We can see here that let's start from this parameter A, and this is independent of flow rate. So eddy diffusion, this is more or less equal and independent of the eluent flow rate. Then B was for the longitudinal diffusion, and we see that longitudinal diffusion is very high when the flow rate is very slow, and this is what makes the chromatographic process inefficient when the low flow rate is very low. So this is the only factor making it high here. Now, at high flow rate range, we see that there are both of those so-called mass transfer factors, and they both influence the high flow rate area and increase the plate height there. And of course, if we sum all those four, then we obtain the curve here, this H here. All right. Are there any questions? I see that questions are coming, are typed. This graph is characteristic for every sample. In a way, yes. So in liquid chromatography, it holds like this. Of course, the numbers are different. Numbers depend on specific conditions, but the shape of the curve is like this. We should find the correct flow rate for every case. Yeah. This question is more difficult than often thought. Okay, let me think. The short answer is no. In principle, when working with relatively small molecules, with small molecules, I mean up to molecular mass about 1000, then the curves are pretty similar. And it's safe to work with a flow rate which we know that works for some compounds. We can use it for other compounds also. When switching to very different conditions, for example, switching to high molecular mass compounds or using very different mobile phases, then yes, it's useful to check whether the flow rate is optimal. So yeah, there is a couple of more factors. Sometimes the flow rate that we can use is dictated by other things than optimal 1 diameter. So sometimes we cannot use higher flow rate because the back pressure in column is just too high. We cannot apply that much pressure. Sometimes detectors are unable to cope with large volumes of liquids. So in short, there are certain traditional flow rates, I would say, for in some applications. And it's useful to check what the literature says, what kind of flow rates have been used for specific setup and compounds, and then it's much easier to choose the correct flow rate. If you check the curve here, then you see that perhaps in this range, it's pretty similar, the theoretical plate height. But this covers quite a wide range of flow rates. So meaning that it's not that strict to get exactly the minimum here on this curve. Okay. So yeah, the short answer was no, we can use traditional flow rates, and this is quite common to do so. Okay. More questions? Okay, you're welcome. Okay, then about those members here, this eddy diffusion curve. This is about several flow paths. And I try to draw it here. What this several flow paths mean? Well, where are the tools? Okay. So I'm trying to draw those. Oh. Stationary phase particles. Okay. Quite a bit of drawing. All right. So let's say this is our stationary phase particles. And of course, within a column, so column walls are here. And Here is the second wall. All right. And this eddy diffusion means that, well, I want to change color. Let's see. Oh, for some reason it made this one red. Okay, let's hope that my drawing will be also red. So if the molecule goes with a flow through the column, then one molecule might go like this. And reach the end of the column. Another one might find its way here and go, oh, quite straight. And of course, as its path is more linear for the second one, then with the same time it reaches further. But if some molecules reach further and others lag behind, this means that the peak is broad. So there are different flow paths in the column, and this causes this eddy diffusion. And no matter what the flow rate is, still this different flow paths in this kind of packed columns are possible. And that's why this A is independent of flow rate. Now, there is another diffusion term, which is longitudinal diffusion. And this longitudinal diffusion, I will try to draw this also. So let's make it with black color. Okay. Another column. It would be so much easier on whiteboard. Okay, so this is the column. I will not mark any solid phase particles in there. Just let's have some molecules, and those are the analyte molecules which initially, when they reach the column, they are in quite a narrow range. But now, as the time passes, of course, molecules from this range, they tend to diffuse, and they can diffuse along the flow and also backwards. So from the high concentration range, the molecules diffuse further. And this means that if time passes means that the front of the analyte moves further, it becomes more diffuse, like this. And the longer is the time that this compound band spends in the column, the wider this band becomes. It just diffuses to both sides. And this makes the column broad. And this is exactly what we see in this range, or see here. on this B divided by U, so this one. And of course, if we increase the flow rate, so take this band through the column faster, then it just doesn't have time to diffuse longer, to diffuse further, and therefore elutes and as a narrow band. So if it stays in a column for a long time, then because of diffusion, the molecules diffuse away from the central band, and the peak becomes broad. But if the flow rate is high, then the peak stays narrow as it initially is. Okay, was this helpful? Or maybe you knew it already. Okay, I hope this was the first question that was helpful. All right. Then let's continue now to the next slide. And this is the second slide where I made slight changes. Because of some technical reasons, some of those lines pointed to a bit wrong places. For example, this line pointed to this U for some reason. So if you printed the slides, then just draw the lines to the correct position, and that's it. No need to print it again. All right, this is the same Van Deemter equation, just that now the factors A and B and C are written in more detail, and we see that this component A, the eddy diffusion component, this contains the diameter of stationary phase particles. So dP is diameter of stationary phase particles, and lambda is a coefficient of uniformity. So if all the particles are exactly of the same size, so the stationary phase particles are of the same size, then lambda would be 1. So the ideal case. All right, now the second term is this longitudinal diffusion term, and we see that it contains the diffusion coefficient of the analyte in mobile phase. Quite like I explained, that the diffusion takes place in the mobile phase. But what I didn't mention on this previous slide, that if the column is densely packed with small stationary phase particles, then the molecules of analyte, they cannot diffuse, because if they do diffuse, they meet the stationary phase particle. So this sorbent, or the stationary phase particles, they help also against the diffusion. So this gamma here is the factor which takes this into account. Then comes the part of the it was mass transfer quantity of this formula. So it was denoted CS, so the mass transfer in stationary phase. And it depends on retention time according to some certain function, also on the thickness of stationary phase layer. And we see that the thickness of the stationary phase can be different, which means also different stationary phase volume. Most importantly, this one depends on the diffusion coefficient of analyte in the stationary phase. So, of course, if this is smaller, then this member will be bigger. If it's big, do we like big H or not? Should H be bigger or no? We like, sorry, I asked in a wrong manner. Do we like big H? No, no, okay. All those who replied no, they like narrow peaks. Very good. And narrow is something that we usually try to achieve. So high efficiency means high number of theoretical plates, but low height of theoretical plate, so low H. Okay. Then last member here is the mass transfer member in mobile phase, and it includes the diffusion coefficient in mobile phase, also the diameter of the stationary phase particle, and again another function of retention time or retention factor. All right. So why do we need this kind of equation, and what can we say from this? So we can decide from here how the stationary phase particle uniformity affects the column performance or the chromatography. So different particle sizes and particle shapes. And we see that if the particles are not of uniform size or uniform shape, then the molecules can travel very differently. They can partition to the stationary phase here and then move along like this. But this is quite different from this particle which travels here and then follows this path. So we would like the particles to have as similar paths as possible. And this can be achieved if all the particles are of similar size. The column is very uniformly packed, so meaning the packing is as dense as possible. And also the particle should be of regular shape. So if the average size is the same, but the shape is different, then this is not good either, because the molecule can go within the voids and between the stationary phase particles and reach the column end too fast. So yeah, this is the reason for requiring small, uniform, well-packed and regularly shaped particles. All right, now a few questions. And how will efficiency change if we? Okay, first of all, what characteristic do we use to tell that efficiency is good or bad? too simple question, or width of peak. N, yes, number of theoretical plates. N another time, or H. Yes, we can use both N or H. If N goes up, then means higher efficiency. If N goes down, lower efficiency. H goes down, higher efficiency. So a bit confusing, but let's just use the term efficiency and say that if we say that something increases, then the efficiency increases, and we mean that number of theoretical plates goes up, or height of theoretical plates goes down. Okay, if we make particles more uniform, so what does this mean to the efficiency? Does it increase efficiency or decrease efficiency? Okay, increase, increase, increase. Yeah. I agree. So indeed, efficiency increases. Okay, but how do we know? If we check the Van Dinter equation, which term in this equation, from which term we see that it increases? So question was about the particles being more uniform. So which term affects the H then? H will have a smaller value because lambda will be 1. Yes. So the first term is affected. So let's write term 1 here. Term 1. All right, let's continue. If we make particles smaller, what happens to efficiency? Increase. More opinions. Increase. Indeed, it increases. Which terms are affected? How do we know that it increases? Okay, particles smaller. Yes, first term. What about the last one? Number 4. Does this affect? And term A, yes. Okay, first and fourth terms. All right. Okay. Now I noticed that the lecture time is over. So please have a look at those questions in this slide, and at home try to figure out how those affect the efficiency, and then we can move really fast next time. Okay. So thank you, and see you on Wednesday. And then those of you who can, please come to the lecture hall. Okay, goodbye.